Hi viewers, in this present class we will discuss contraction joints, expansion joints. First we will see contraction joints and then we will go for expansion joints and longitudinal joints, tie bars and double bars. So contraction joints, see this is a CC rod which is divided into blocks, right? You know, divided into blocks. So this is a longitudinal joint along the pavement and these are contraction joints. Say these are contraction joints, and after a few contraction joints you will find expansion joint, and here also after a few contraction joints you will find expansion joint. So you can observe while traveling you will get a sudden jerk because of the gap that is there here. So we have expansion joints after a few contraction joints. So all these are contraction joints. So expansion joint, you can observe while traveling you will get a jerk and filler will be filled in the contraction joint even though you will find a jerk. Now how to determine the length between these contraction joints, that is spacing between contraction joints and spacing between expansion joints. So expansion joints, suppose this is length between expansion joints, and we know that strain is equal to change in length by original length, right? And change in length, because of the temperature the concrete is going to expand, so this change in length is multiplication of coefficient of thermal expansion into temperature difference. So within a period, what is the maximum temperature that can be obtained in that particular pavement on that surface, and similarly minimum temperature, that temperature difference into coefficient of thermal expansion. So that is in per degree centigrade. That is in per degree centigrade, and generally this is 10 millionth. That is 10 into 10 power minus 6 per degree centigrade, and from this you can find length as, so length between expansion joints as so we got delta as C into T2 minus T1 into LE, and from this LE is delta, that is this spacing, that is change in length is the spacing divided by C into T2 minus T1. This is about expansion joint. Now what about contraction joint? And also in this you have to observe this filler, whatever is filled inside between these joints, along this joint, this filler may be assumed to be only reduces by 50%. So if they give the data like delta is 2 centimeter, that is gap between expansion joints, If it is only contracted by 50%, then you have to take not 2 centimeter, you have to take 50% of it, that is 0.5 into 2 centimeter. You have to consider 1 centimeter here. So I put lambda dash because of this one. And now we will see contraction joints. So suppose this is one particular block. And let B is the width. So this is width and this is length. And we know H is the slab length, height of the slab, concrete slab. Now what happens is the construction temperature is different, and the temperature, as the temperature decreases, the slab tries to contract, right? The slab tries to contract. And that contraction is counteracted by the self weight. So therefore, allowable stress, tensile stress in concrete. So because the contraction is restricted, during curing we know the shrinkage happens, right? So therefore, we are counteracting that shrinkage. So there exists tensile stress in concrete into cross sectional area. What is that? B into L, H. B into H, that is equal to gamma, that is unit weight of concrete, into friction factor, that is happening here, friction factor here, into, so we know this contraction or expansion is happening within the concrete slab, so we have to consider 50%, that is L by 2 here, L by 2 here. So L by 2, we will put LC, that is contraction, into 2 into B to H. Now you find out what is length of this contraction joints, that is between contraction joints, what is the length. So B into H gets cancelled and you will get 2 into tensile stress of concrete, allowable tensile stress of concrete, to gamma into F. And if at all steel is used here, so steel is used along this transverse joints, if steel is used, then what happens? Instead of tensile stress of concrete, the tensile stress is replaced by steel. So this equation becomes, so allowable stress of tension for steel into area of steel, whatever steel you have used, area of steel, that is equal to same. And then you have to find, so this we have replaced by this, then you have to find length according to this formula. Right? So area of steel, you assume some diameter of the, you assume diameter and spacing and find total area of steel and do this equation. By using this equation you find length of this contraction joint. And then what is this? We know concrete is very low, having very low stress, that is 0.8, kg per centimeter square. Similarly here, this can go up to 1400 kg per centimeter square. And if you observe, once you calculate an example, then you will be understanding that this length of contraction joint here and here, you will get a higher value. You will get higher value. That means length between contraction joints gets increased because of using of steel. So if it is clear up to now, then we will move to tie bars. So tie bars are used along the longitudinal joint here. So if it is a two-way slab, that is two-lane road, if it is a two-lane road, we have two lanes. That is 3.6 here and 3.6 here. Then here also, this is also a contraction joint, but we are tying two slabs in the longitudinal way, so we call them tie bars. Tie bars, and here also, because of the contraction, here what happens is, you have to find out, assume some diameter, and you have to find out length of tie bar and spacing. So you assume some diameter of tie bar, and then you have to find length and spacing. Now what happens is, see, suppose this is the longitudinal joint and here are the rods. Now since this gap is very small, you can ignore that gap and you can take this length of rod as LT, that is length of tie bar, and 50% here and 50% here. You have to consider LT by 2. Into here bondage between steel and concrete is there. So that bond stress between steel and concrete, and the perimeter of the rod, perimeter length will gives you the surface area. Perimeter and length will give you the surface area, and this is bond stress between concrete and steel. And if you use deformed bars, you will get a higher stress. If you use plain bars, it is lower. And now this should be equated to, so we will consider 1 meter length. We will consider length as 1 meter. So that is, you will consider length as 1 meter. And for single rod we are calculating, so allowable stress of steel in tension into cross section area of single bar. Whatever the cross section area of single tie bar. Now you get some value for length of tie bar. And then you consider total area of steel per length per 1 meter into that is equal to, as we have already discussed, gamma F, and L we are taking 1 meter, and then B to H. And from this you will get area of steel in centimeter square per meter, right? You have considered 1 meter, area of steel in centimeter square per meter, and then you have to find spacing as you have done in your reinforced concrete structures. Spacing is given by area of individual steel bar divided by area per meter length. You will get it in meter, right? Then if you calculate this one, perimeter is pi d, and this one is pi by 4 d square, and upon calculation you will get this as d to ss by 2 into sb, where ss is allowable tensile stress of steel and bond stress between steel and concrete. So try to remember this formula. Now we will move on to dowel bars. So dowel bars are used along this transverse joint at wherever expansion joint is there. Suppose this is a concrete slab, CC pavement slab, and this is the another slab. So this one and this one. So wheel load is moving from one slab to the other slab. So there is sudden load transfer from this slab to this slab. So the deformation may happen and undulations may happen between the slabs. So for load transfer, what we do is, because this gap is there, we use steel rods. In between the steel rods here are called dowel bars. Dowel bars, suppose this is delta, that is expansion joint, and total length of the bar, dowel bar is L, then effective length, that is whatever length is embodied inside the concrete, is L minus delta. This is embedded length and this is total length. Embedded length and total length. And then how to find out this length? So as per Brad buddies, we have this rod may attain shear stress. So there can be shear in the rod, or there can be bending of the rod. There can be shear, there can be bending of the steel rod, and then there can be bearing in concrete. So there can be bearing of concrete. So shear, bending and bearing, we have given three formulae. So 0.785 d square into Fs, where Fs is the allowable stress, allowable shear stress in steel. Similarly, this one we have 5d cube F bending, that is, you can also call it flexure, divided by LD plus 8.8 delta. Similarly, for bearing of concrete, for bearing stress of concrete, we have and is FB. So we have allowable stress, shear stress of steel, allowable flexural stress, that is bending stress of steel, and allowable bearing stress in concrete. We have three criteria, and from these three criteria, first you have to equate these two equations by assume some diameter, assume G, whatever diameter, and we have expansion joint, we have delta, D we have, delta we have, then equate these two equations. If you equate these two equations, assume D and we have delta, if you equate these two equations, you will get LD as 5D FF divided by FB and D. So this is in numerator, LD plus 1.5 delta divided by LD plus 8.8 delta whole power 1 by 2. And then you will get this LD. So length of double bar we just found out, and then this, using this length we got, and then we need spacing. For spacing, what we do is, this dowel system will only take care of 40% of the design wheel load. So whatever design wheel load, this dowel bar system will take 40% of the design load, and then this E dash, whatever we got from these three values, you have to take lowest value, adopt lowest value, and then this dowel system is assumed to withstand the load linearly, either side linearly, only up to a distance of 1.8 L, 1.8 times L, where L is radius of relative stiffness. You know that? Radius of relative stiffness, that you know, EH cube by 12K into 1 minus mu square whole power 1 by 4, that we know. So linearly it will decrease. So what we do is, you find out capacity factor, that is equal to 40% of design load, using 40% of design load, and this P dash, using this, and once using capacity factor is that, you got the capacity factor, and using this linear variation we can find out spacing between dowel bars. So we will do one example, then you will be able to understand how to find out the length of contraction joint, length between contraction joints, expansion joints, and spacing, and also the dowel bars. We will solve that in the next session.